Good morning. So today's topic will be state reduction and sequential circuit analysis. Last lecture we already talked about the design, and through the design, one of the steps, if you can make some state reduction, which is reduce part of the states that's maybe repeated or unnecessary. So last lecture we skipped that step. Now we want to talk about how do we do the state reduction. So, important announcement, quiz 5 has been moved from Wednesday, July 25 to Friday. From Wednesday, I think July was 27. It was removed. So now the new date is July 29. Okay? And that quiz will be open notes for your information. And it will be everything we covered after the second test. And there is a homework number 8 that associate with analysis and some design and sequential circuit analysis. So homework number 8, you can go to Canvas files, homework number 8. So try these problems from the textbook. Then for this part, you will see the answers we already provided, the final answer. So try to do them at home and compare this with the final answers. Okay? Now, let's go to today's topic, which is the state reduction. So what's state reduction, why we need it? So the process of reduction, the state reduction, because sometimes we have some additional states or some repeated states. So these states, when we have multi-states, this means multi-flip-flops. So if you find a way to reduce the number of states, then reducing the number of flip-flops, reducing the complexity, reducing the cost. So the number of flip-flops determined as the number of the states related to the states, or related to the states. There are, I think, two power number of flip-flops will equal to the states. So yeah, here's a sequential circuit that has m flip-flops, then 2 to the power m are the states. So the state reduction, the number of states, we might or we might find a way that we can reduce the number of states, which means reducing the number of flip-flops. For example, let's assume we have this state diagram. And for this state diagram, the input sequence is, the initial state is A, and the input sequence 0, 1, 0, 1, 0, 1, and so on. So, by following this state diagram, we are at state A, input 0, the output is 0. Then if the input is 1, we will go to state B, and the output is 0, and so on. Just follow the procedure. We will see that each state we will go to next, for example, B, then we will go to C, then D. We already talked about how to do this stuff. So when we look at these states, we might see some repeated or unnecessary stuff. So let's talk about this one. Okay. So when can I say, or when can I make state reduction? By removing or replacing one state by other. So we can say two states are said to be equivalent if each number of inputs gives the same exactly as the outputs and sent to the same states or equivalent state. So let's have some observation here. Is there any states that have the same input and same outputs, for the same input give the same outputs? We can see many, but we need to look also at the states. So by looking here at the states G and state E. So state E will give us, if the input is 0, to state A. If the input is 1, we'll go to state B. And if the input is 0, will be at 0. If the input 1, will go at 1. And for G, if the input is 0, we'll go to A. If the input is 1, we'll go to F. If the input is 0, output is 0. If the input is 1, output is 1. You see, they are the same. The same outputs, the same inputs, the same states. Then we can say these two states are equivalent, because when the input they give the same inputs, or at the same inputs will give us the same output and the same next states. That's it. Then we can say E and G are equivalents. So the first point we can make observation, look at the outputs. Look at the outputs. If those are the same, go to the next, which is look at the outputs. If those are the same, look at the next states. If they are the same, then we can say they are equivalents. If they are not the same, you need to look at the state itself. Does it give the same as state itself? If yes, then we will say equivalent. If no, then they are not equivalents. Okay, not equivalents. What do I mean by this? The first step, look at the inputs and outputs. So we will see like 1, 2, 3, 4. 4 states are sharing the same input and same outputs. So what we need to do that next, by looking at the next states. So at input F, they are all, or at input 1, they are all F. Let's look at this input. So here D will give us E, E will give us A, so those are not equivalents. How about here? E will give us A, F will give us G, those are not equivalent. Then we can say E and G are equivalents. So that's how we make it something we call it by observation. Okay? How about 0 and 0? Is there any equivalence? 0 and 0 and 0 and 0 here. So here will give us A, here B. This is different. Here B, D, A, D. Those are not the same. There is nothing at the same here. A and C. Let's see here between A and B. Here between A and D. Those are not the same. Okay. Let me have a look between D and F. D and F. D between 0 and 1, 0 and 1. Here between E and F. Here between G and F. Okay. So D, E, and G. Okay. And we already talked about E and G are the same, right? So that's why we can say D and F are the same. So when you need to pay attention a lot when you do this state reduction. So after doing the first reduction, we will find that those are the same. How can we replace those? The first parts, let's assume that we don't know about D and F. Let's replace E and G. Okay? So by replacing E and G, redraw the same table and substitute. You might choose D or you might choose F. I'm sorry, you might choose E, you might choose G. Let's get rid of G and replace every G by E. So we will remove this part like it's not exist. Then rewrite the table. Here's we rewrite the table. And we replace any G in this circuit, replace it by E. In this table, replace it by E. So here there was a G, replace it by E. So if there was a G, replace it by the G replaced by E. Then by looking at this table, this new table, we will see that D and F are the same. Okay? Then Let's remove f and replace every f by d. Then do the next simplification. We have a, b, c, d, e, and here every f will be replaced by d. Let's have a look here. Is there any equivalent circuits? Is there any 0, 1, 0, 1 between E, D, A, D? No. 0, 0, 0, 0, there is no. So this is the lowest reduced state table. Okay? Now, with the new reduced state table, let's draw the equivalent or the state diagram for the new circuits, for the new table. So we can say that here is state A. If the input is 0, will remain at A and the output is 0. If the input is 1, will go to B and the output is 0. Now with B, if the input is 0, will go to C. If the input is 1, it will go to D. Oh, you should tell me about this. I apologize. If the input is 1, it will go to D. Now, with C, if the input is 0, it will go back to A. If the input is 1, it will go to D. Now, with D, if the input is 0, it will go to E. If the input is 1, it will remain at D and the output is 1. Now, with E, if the input is 0, it will back to A. If the input is 1, it will go to D. And the output is 1. Okay? Now, let's recall when we did this state table and this state table. Let's make a comparison. Now we claim this table is the same as this table. How can I guarantee this? I mean, we already done this process, but how can we validate this? We can validate this by testing the sequence of inputs. So we have tested the sequence of inputs here, and we see how much the outputs and how much the new states. How are the new states? How are the outputs? How about with this system, if we test the same inputs, will we get the same sequence? If yes, then my state reduction is correct. If no, then there's something wrong. How can we validate this? Let's apply the inputs here. Here is states. Here is inputs. Here is outputs. So the initial state was state A, and the input sequence, let me copy it, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. Okay. Now, I want to cover this, and I want to deal with this table. Then I want to find my final answer and compare it with the original table. Then we will see. Now, the input is 0, the output here is 0. Okay, so we are at state A. Then the next, when I go to A, when the output is 1, I will go to, or here the input is 0, I will remain at A, because the next state will be A, and the output will be 0. Now the input is 1. When the input is 1, I will go to B, and the output is 0. Now I'm with B, the input is 0. Where should I go? To C, right? Yes. And the output's 0. Now I'm at C. The inputs is 1. Where should I go? D. And the output's 0. Now I'm with D and 0. Where should I go? E. And the output is 0. D, E. The output is 0. Okay, now I'm at E, and the inputs is 1. Where should I go? D. The output is 1. I think here just I have I want to make a correction. Let me go back. When here I'm D and the input is 0, I will go to E. Then the input here is 1, then the output should be 1. Because 1 over 1 will go to D. Okay? Then I'm at D, the input is 1, and the output is 1. Then I will remain at D, right? Now I'm at D, the input is 0, the output is 0, I will go to E. Now I'm at E, the input is 1, the output is 1. Where should I go? D. Now at D, the input is 0, the input is 0, the output is 0. Then I will go to E. Now at E, the input is 0, the output will be 0, then the next state will be D, or I'm sorry, will be A, I'm sorry, because 0, 0, A. So there is no other inputs. So let me compare this. Is it the same as the old one? So let's see. A, B. Okay. Like this. A, B, C, D, E. Here is D, but we said D equal to F, right? So D equal to F, E, and let me say, do we say D and F here? G equal to E. This should be G. This is equal to G. G equal to E. D equal to F. E equal to G. Then A. Let's look at the outputs. 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 4, 5. 1, 2, 3, 4, 5. Then 2 ones, 2 ones. 0, 1, 0, 1, 0, 0, 0, 0. Then they are the same, right? So that's how state reduction works, which is instead of dealing with this complicated, this steps, and with this complicated step means more states, more flip-flops, more complicated circuits. When I want to do the kernel maps will be very complicated. I have 1, 2, 3, 4, 5, 6, 7 states, which means I need almost 4 flip-flops. Then since we have 1 input, I need to make 5 kernel maps, 5 state kernel maps. So this will be large. While when we have 1, 2, 3, 4, 5, this means even 5, I still need 4. Sometimes, if I find a way to make it 4, then I need to use 2 flip-flops so I can make 3 kernel maps, 3 variable kernel maps. Okay, so just reducing the complexity, sometimes reducing the flip-flops, sometimes not, depending on how the state reduction will be. Okay, any questions? So this table summarizes what I talked about. Again, so the same output sequence, even though the state sequence sometimes can be different because we replace D by F and E by G. Okay? Any questions? Now we can find how to do the state reduction. We can do it in 2 ways, which is the inspection, the way that I talk about this, and we have something else we call it implication table. So how can we do the inspection first? So let me give more examples to make sure that you get the idea. So inspection, which is the simplest techniques and the most maybe obvious, we can see it by inspection. By looking at this circuits or this design, we will see that this one, state A, give us 0, 1, 0, 1, 1, 0, 0, 1. So state C, there is no way to reduce it because it's 1, 0. Then we have 3 states. We can make state reduction, which is this 0, 1, 0, 1, 0, 1. Let's look at state A. It's between B and C. State B between C and A. D between C and A. So we can say that those are the same between B and D, right? So we can say B and D are the same. So replace Let's remove D, replace any D elements by B. So we will write it as this one B over 0, C over 0 the same. This one C over 0, A over 0 the same. This one, instead of D, we will write B because replace any D by B. Replace any D by B, so this will be B, this will be B. Okay? Understood? How about another example? We have here A, B, C, D. So let's look where are the output are the same. So the output 0, 1, 0, 1, 0, 1. So we need to look at A, B, and D. C is not included. Then we can say that here B between B and A, this is between B and C. So there is no way between A and B, right? Difference in two. Let's look between A and D. B, D, here A. So there is no way between A and D. The only remaining between B and D. So B in this part, A and A, those are the same. How about this part? Those are not the same. Well, let's look at the procedure I wrote. If they are not the same, does it have the same itself state or the same state? I mean, does the next state of B is B? Yes. Does the next state of D is D? Yes. Then we can say these are equivalents. We can, if it is, we can say in this part, does next state of B is B, or next states of D is D. Then yes, that's why they are equivalents for the other parts. Okay? So there are two ways. If they are the same states, like this one AA, or if they are the next states is the same as the state itself. So my next state is to remain at B, and the other state, the next state is to remain at D, then this gives us the same meaning. Okay? So we can say these two equivalent. Then replace D by B, any D by B. So let me redraw the states diagram. This one is written in Mealy model. So here state A. Then I'm going to write here B over 0, C over 1. Here is state B, B over 0, A over 1. Then state C. We no longer have D. Replace every D by B. So it will be B over 1, then B over 0. Then D has been removed. That's it. Okay? Any questions? Now your turn to try this example. Make the state reduction and tell me where are the similarities, or what are the states that we consider equivalents. Okay. It's by inspection, so we should get it fast. Okay. Is there anybody find an answer or no? B and D. Right. How? The first observation, look at the outputs. So 0, 1, 0, 1, 0, 1. So there is no way for C to be in. Then the second part, look at the inputs. If there's any input are the same. So C, B, D, A, D, B, and this one we see excludes C. B, A, D, A, B, C. So here, B, C, there is nothing about the state itself or the other state. So we can exclude A. Let's look at B and D. So here is A, these are the same. Then the second part, B will go to D. But let's wait. This is not the same as the states, but it's the same as the other states. So we can include, is it the same as the next state? Is it the same state or the same as the other states? So these are the third option, the third way. Okay? Then we can say these two are equivalent. So we can say, is it equivalent if those are the same next states or the next states is the state itself, or the third part, which is the next state is the other states. Then we can say these are the three conditions. There's no fourth condition for that. Just these are three. If you understand them, then you should get it right. Okay? So how can we replace this? States. Here is x0. Let's replace. Now I want to remove B and I want to keep D. So replace B equal to D. I want to remove B. You are free. You can replace any states. But I just want to do this to see. So here is state A. Don't put any B. I want to just put for every B, make D. So this will be D over 0. This will be C over 1. This will be, there is no state B. Let's go to C. Here will be D over 1. And B will equal to D, which is D over 0. Now here is state D. So every B replace it by D. D over 0, A over 1. Okay? Is this clear? Any questions? Is there anybody that didn't get it? Didn't understand it very well? Okay, so you need to be familiar with these three conditions. So the first thing, when you make the observation, look at the outputs. Then the next step, look at these next states. Is it the same as the state itself, or the same as the next states, or the same next states for every case? Now, how about the other method, which is called implication table? So we can find here these tests. Whenever we have larger table, it will be more complicated to do, especially when we have multi-inputs. How about when we have 4 inputs or 2 inputs? How can we deal with this? This will be more complicated. So how can we deal with this? The inspection sometimes can be very difficult. In this small table, yes, we can find it easy. But how about we have more complicated states, more complicated switch, which is most likely the real time or the real applications, real life applications are more complicated than that. So we can use some methods. It's called implication table, which is we need to follow some procedures to do how to do this simplification. So this is called implication table, which is used for complex states. So it can be applied incompletely for specified sequential circuit. We can apply it for some sequential circuits to do some analysis. So what are the procedure? Let's have a look here. So we need to look at the state table. Whenever you have any state diagram, convert it to state table, then we can do the process. The first thing, which is list all state vertically except the first and horizontally except the last. Then the resulting will display all possible combination of the states. So we need to make something is called implication table. How can we do the first step? Let me assume that we have states from A, B, C, D, E. We have these states. How can I apply step number 1? So replace all state except the first one vertically. So we will say, let's remove the first one. Let's make B, C, D, E. I'm gonna write here B, here C, D, E. This is vertically. Horizontally, make all of the state except the last. Let's make A, B, C, D without E. So let's start here A, here is B, here is C, here is D. Don't write it, because the last we don't want to make it. Then let's make the possible combination by creating a table. It's called implication table. How this table being created? We will make this. Let's make this row, make this row. Then make this column, make this column, make this column, make this column. So we'll create this table. Again, here is the states B, C, D, E, removing the first one, and here is the states, removing the last one. Okay? This is the first step. Second step, only states with identical inputs can be equivalents. If there is any states with different input, we cannot apply. Which is, let me talk about, for example, these parts. When there is any state that difference, we can cross it. Actually, so since this, I just want to talk about this, the procedure, then we will see an example. But I mean, when the outputs are different, look at the output, make states A, B, C, D, E, and look at the outputs when, for example, x equals 0, x equals 1, and see. If the outputs, for example, are different, let me assume this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1. So here between A and B, let's look at this cell. Does A and B have the same outputs? Yes. Does A and C have the same outputs? No. Cross it. Does A and D have the same outputs? No. Cross it. Does A and E have the same outputs? No. Cross it. Does B and C have the same outputs? No. Cross it. Does B and D have the same outputs? B and D. No. Cross it. Does B and E have the same outputs? No. Cross it. Does D and C? Yes. Keep it. D and E? Yes. Keep it. E and D? Yes. Keep it. So the crossed states, which means there is no way for them to be as equivalents. Then we will go to here to replace the states, or not replace, the pair, the next state. Let's look at the next state table. Then we will see something is called, is it implied or not? If these two states are implied pairs, which has the only the states that define the cell itself, or the next states, if these, by looking at the table, if these cells contain the only state that define the cell, which is the cell states, or they are sharing the next states, or the two states are the same, then we can make a check mark on it. Then we can cross the contents that has at least one implied pair that crossed out in step 2. So we need to create something that's called implied pairs. I will mention this in an example, because in this example I don't think I can represent this. Then we can reduce by trying to reduce the possibilities. After reducing the possibilities, we can find one of the pairs or two of the pairs are the same. How? Let's see this example, example number 1. Then I think the situation should be easier with dealing with this. Reduce the following table using implication table. The first step, look at the states A, B, C, D, E. We have 5 states. So let's build the implication table. So step 1. when we want to build the application table, we need to start vertically, which is remove or don't include the first state, which is here B, C, D, E. And horizontally, all of the states removing the last one. So we will say A, B, C, D. Here is A, B, C, D. Then make the table. Okay. After that, let's go to step number 2 to cross the states that are not sharing the same output. So what I encourage you to do, to redraw the table by including only the outputs. Here is A, B, C, D, E. And let me write the output, which is here 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. So between A and B are those have the same? Yes. So no crossing. A and C the same. Don't cross A and C. A and D are different, so cross it. A and E are different. Cross it. B and C are the same. Don't cross. B and D, cross it. B and E, cross it, right? How about D? D and here C and D. C and D are different. Cross it. C and E are different. Cross it. D and E, same. So don't cross it. So we end up having 3 uncrossed steps, right? So what should we do now? Next, let's make step number 3 by making the implication pairs. What's the implication pairs? So we need to make the table with the next states. Let's make the table states. And here is x equals 0, x equals 1. Let me redraw the table A, B, C, D, E. So the next state with A, here C, B, C, E. Let me write them. Here is C, B, C, E, B, E, D, B, E, A. Actually, you don't need to write this. You can compare this here, but I'm doing this for simplification. I mean, during the tests, you don't need to do anything. You don't need to do this. You can compare it from here. But I'm doing it for simplification. So we need to find, we call it, look at each states on this one. Let's make another table, and we need to find the implication pairs for every element. Okay. Now, I think there's something here we need to do. Okay, so we have, by looking at these elements, we have this 1, 2, 3, 4 squares, right? Are not crossed. Is that right? So this square, we have 4 squares, are not crossed. We have AB square, AC, and BC, and the last one, which is DE, right? So let's look at AB. A and B. Or here, A and B. A between C and B, B between C and E. So are those the same? Are those the same or not? Are those the same or not? Not, no. Because here C, C. Even though this is B, but this is not A. If it's A, then we can do the same, right? But these are not the same. So what should we do? We can say C will give us, or A will give us CB, B will give us CE, right? So those are fine. But the problem with this, okay? So this problem, take this column, and we will say what caused the problem is BE. Okay? This is the reason for not being the same as BE. This BE will be called implied, the implied pairs. Okay? How about the next, which is AC? A and C. A and C, A will give us CB, C will give us BE. Okay. So here, those are not the same, right? They are different here and different here, right? So take them as a column and make them in alphabet. So the implication pairs are two, which is BC and BE. Let's look at the other pair, which is BC. BC. So B will give us CE and C will give us BE. So E is fine, E is fine. Here, this is C, which is equivalent to here. This is B equivalent to here. So we can say those are fine. So those are equivalents. So we'll put check mark on it. Okay? How about the last pair, which is DE? D and E. D will give us DB. E will give us E and A. So this is D, the state itself, and E, the state itself. So those are fine. But the problem is with these two. Then the implication pairs are AB. Okay? Does everyone understand this? How to find the implication pairs? Okay, now insert this to the implication table. So we will say that here is BE. Here is at AC we have BC, BE. Here is BC, BE. And in BC, this part will be check mark. Then in DE will be AB. DE, here is AB. Okay? So after determining those and writing them in the table, now let's try to make exclude some stuff, which is by removing the pairs, removing the pairs that we crossed out. How? Look at BE. Did we cross BE? Here is B, here is E. Is it crossed? Is that right? B is crossed, right? Then this one, exclude this by writing this. Look at BC. Is BC crossed? Here is B. Here is C. No, it's not crossed. But let's look at BE. Is BE crossed? Here is B. Here is E. Yes. So we cross this as well. This one is BC. Is BC, or when there is a check mark, then don't worry about it. Let's look at AB. Look at AB. Is AB crossed? Here is A, here is B. It's been excluded here. So, excluded. Why? Because it's excluded here as well. Okay? Then the only left element is what? Where there is a check mark here. Right? So, the only left elements is state or is BC. Right? This BC block. Then we can say B and C are equivalents. So let's redraw the table or redraw the state diagram. So we can say here B and C are equivalents. Then replace every C by B. So, or you're free, you can replace every B by C. So it doesn't matter. States, here is X, 0, 1. Here is A, B. I'm replacing C, we have D and E. So A will be, since it's C replaced by B, will be B. B over 1, B over 0. Here will be B over 1, E over 0. C has been removed. Then here D over 0, B over 1, E over 0, A over 1. And that's it. Problem done. Any questions? Is this clear? So the complexity we found is in determining the implication pairs. I think this is the most difficult part. So we will go more examples, then I think the problem should be easier with this. Let's see example number 2. Reduce the following table using implication table. How many states do we have? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 states. So let's make this implication table. Start with remove the first alphabets, which is A, and make vertically B until H, horizontally A until G. So here is B, C, D, E, F, G, H, and here is A, B, C, D, E, F. Okay? Oh, G, sorry. G. Then let's start make this line, and with B here. Uh-oh. Okay. Like this. Now, you can look at the table or you can make your own by looking at the states and the outputs. A, B, C, D, E, F, G, H. So with A, we have 0, 0, B, 1, 0, E, 0, 1, then D, 0, 0, E, 1, 0, 0, 1, 1, 1, 1, 1. Okay. Then let's see. A and B, are those the same? No. Cross it. A and C, are those the same? No. Cross it. A and D, are those the same? Yes. A and E, are those the same? No. Cross it. A and F, are those the same? No. Cross it. A and G, no. Cross it. A and H, no. B and C, are those the same? No. B and D, no. B and E, yes. B and F, no. B and G, no. B and H, no. Now C and D, are those the same? No. C and E, no. C and F, yes. C and G, no. C and H, no. How about D? D and E, are those the same? No. D and F, no. D and G, no. D and H, no. How about E? E and F, no. E and G, E and H. How about F? F and G, no. F and H, no. How about G? Yes. Okay, so the next step, let's draw the state table with the states. So here is A, B, C, D, E, F, G, H. Then at input 0, or here for state is ED, I'm going to copy from the table AF, CA, BA, CA, BA, DC, then CD, then HG, then CB. Okay? Then let's look also at the blocks that are lifts. So we have 1, 2, 3, 4. 4 blocks. So these 4 blocks are AD, then BE, then CF, then GH. Okay? We prefer to put them in the alphabetical order. So we don't prefer to say HG, we say GH. Okay? Now, let's make the implication pairs to find for them. So for AD, here is A, here is D. For A, it's give us E, D. For D, will be B, A. So it will not give the same state itself or the next state. So we have a problem here. And here, the states, the next states, or the other state. So these are fine, right? Then we have this element. So the application table for this part, or the application pairs, are BE. Okay? Did you get it? Okay. How about BE? So for BE, B will give us AF, E will give us DC. The next states are not the same. Here are not the next states. So we have a problem with this and with this. So we have 2 pairs. We have making in the alphabet order. First, take it as a column and make everyone on alphabet. So AD, and we have this one is what? F, yes. CF. Okay? Now, let's look at the third, which is CF. So C will give us CA, F, CD. So both are C's, which is correct. Here, A and D are, we have a problem with this, right? So it's the here are AD. Okay? Let's go to the last pair, which is GH. Here's G, and here is H. So for G, it is HG. For H, it is CB. So we realize that there are no similarities for both. Then it will be written as CHBG. Okay? Is this clear? Now, let's write them into the table. So for AD, we have BE. I'm going to write here BE. For BE, ADCF. ADCF. For CF, it is AD. For GH, it is CH and BG. Okay? Now, let's see. Between A and D. Between A and D, we have BE. Look at BE. Is BE crossed? BE, is it crossed? No, it's not crossed. Let's keep it. How about AD? This one, AD and CF. AD, is it crossed? No. CF, here is C and F. Is it crossed? No, let's keep it. How about CF? I mean, here at CF, which is AD here. Is AD crossed? Here is AD. No, so don't cross it. How about this one? CH. C and H. Is it crossed? Yes, so let's cross this. Or just put this line as indication as being crossed. Therefore, we can conclude we have 3 blocks and 3 blocks left or uncrossed. Uncrossed. What are these 3 blocks? Which is AD, BE, and CF, right? Then we can say these 3 blocks, A and D are equivalent, B and E are equivalent, C and F are equivalent. We can say A equal to D, B equal to E, C equal to F. That's simple. So we can redraw the table. So redraw the table by replacing. You are free. You can keep A or keep D. So what I prefer is to make every D equal to A, every E equal to B, every F equal to C. Therefore, let's redraw the table. Here is state, here is x, 0, 1. So we have state A, then it's equivalent to E. So we will replace E by B, B over 0, and D is left, D over 0. Then state B, B equal to A over 0. Then F equal to C, so C over 0. Okay? I'm trying to rewrite this. So here is E. We said E replaced by B. That's why B over 0. Oh, D over A. I'm sorry about that. Thank you. D equal A over 0. Here is A over 0. Here is F equal to C over 0. Then we have C. Here, C over 0, A over 0. Then D has been replaced. E has been replaced. F has been replaced. Let's go to G. G, here H over 1, G over 1, H, which is C over 1, B over 1. Okay? So now, this table has been simplified using 8 states to be 1, 2, 3, 4, 5 states. Then this will make the life easier. Okay, understood? Any questions? Okay, that's great. Now, let's see another example. But how about if we have multi-inputs? It will be more complicated. Still, before starting the third example, any questions? Okay. So we have this state diagram. Then we have 1, 2, 3, 4, 5, 6, 7, 8. 8 states. The first step, make the implication table, which is from A to G, or from B to H, vertically, horizontally from A to G. So vertically from B, here's C, D, E, F, G, while here H. Here the other part horizontally A, B, C, D, E, F, G. Then make a line this way, make a line this way, then start drawing. Okay? Now, the best way, what I do recommend, you can look at the table, but I do recommend to separate the tables or to make sure that we can compare easily. So we have here states, here are the inputs 0, 0, 0, 1, 1, 1, 1, 0. Then here is A, B, C, D, E, F, G, H. So here 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0. Then for E, 1, 0, 1, 0, F 0, 0, 0, 0, G 0, 0, 0, 0, F 1, 0, 1, 0. Okay? Now, let's try to cross the cells that are not the same. A and B are not the same, right? Cross it. A and C, cross it. A and D, yes, keep it. A and E, cross it. A and E, right? A and F, keep it. A and G, keep it. A and H, cross it. How about B? B and C, keep it. B and D, cross it. B and E, keep it. B and F, cross it. B and G, cross it. B and H, keep it. How about C? C and D, cross it. C and E, keep it. C and F, cross it. C and G, cross it. C and H, keep it. How about D? D and E, cross it. D and F, keep it. D and F, yes, keep it. D and G, keep it. D and H, cross it. How about E? E and F, cross it. E and G, cross it. E and F, I'm sorry, E and H, keep it. How about F? F and G, keep it. F and H, cross it. How about G and H, cross it. Okay? Now, how many blocks left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 blocks left, which are AD, AG, BC, BE, BH, CE, CH, DF, DG, EH, FG. Okay? Now the next step, make the state table with the states alone. Here is state A, B, C, D, E, F, G, H. Now this one is D, D, F, A, C, D, E, F, C, D, E, A, D, B, A, F, C, F, E, A, G, G, A, B, D, A, E, A. This is the table. I just copy it from this part, from this one, to be including only the states. Now, we need to look at the implication table for each states, or the implication pairs, sorry, for each states.